In Canada, indoor ice rinks are more than just recreational spaces. They're a cornerstone of our culture. From community arenas to world-class stadiums, they are where future hockey legends are born and where our nation's passion for winter sports is celebrated. With over 3,000 indoor rinks and 800,000 registered players, these spaces have united communities across the generations, helping define what it means to be a Canadian. Yet, their operations come with a growing cost. Ice rinks require a surface temperature of -8 degrees Celsius to remain solid. However, surrounding areas like spectator stands and lobbies are kept much warmer, at around 15 to 20 degrees. This creates a temperature imbalance, forcing rinks into a continuous struggle to keep ice from melting. To counteract this, ice rinks rely on large refrigeration systems to maintain sub-zero temperatures. However, as heat constantly infiltrates the rink from surrounding spaces, these systems must work harder, consuming a significant amount of energy. The average rink uses 520 kilowatt hours of energy every day, equivalent to the monthly energy consumption of an entire household. Half of this energy goes solely towards refrigeration, contributing to rising carbon emissions and financial costs for rink operators. Current solutions involve synthetic polymers as a replacement for traditional ice, eliminating the need for refrigeration. However, these materials cause increased friction, blade dulling, and restricted movement, compromising skating performance. With the sustainability of these rinks and the Canadian identity under threat, it is crucial to develop a solution that will reduce refrigeration needs while preserving the skating experience.
We are RHS-Calgary, and our approach redefines rink maintenance by enabling ice formation at higher temperatures. We plan to use ice nucleating proteins, molecules that can trigger ice formation at temperatures up to -2 degrees Celsius, 6 degrees warmer than current rink temperatures. These proteins, naturally produced by the plant pathogen Pseudomonas syringae, consist of small dimers that replicate the structure of ice crystals, allowing water to freeze around them. These dimers are made up of repeating 3 amino acid motifs containing hydrophilic and hydrophobic groups. Hydrophilic groups attract water molecules to the protein, while hydrophobic groups trap the water to stabilize the crystal. INPs in Pseudomonas syringae have been extensively studied for their role in plant infection, with the ability to trigger ice formation at higher temperatures. To harness this ability, our team plans to engineer E. coli with INAZ genes to produce recombinant ice nucleating proteins. In P. syringae, these proteins are naturally anchored to the cell surface. To optimize their use, we will modify the protein structure by removing the membrane-bound regions, enabling E. coli to secrete the proteins efficiently. We will also modify the N-terminal of the protein to enhance aggregation, increasing nucleation. Once secreted, we will purify the INPs from the cell mass and apply them directly to rink surfaces. This approach will allow us to maintain ice formation at higher temperatures, significantly reducing the excessive energy required for refrigeration.
We plan to simulate ice nucleation using GROMACS to analyze the molecular structure of INP-induced ice. Additionally, we will model the effects of removing membrane-bound regions and other protein modifications on nucleation efficiency. So far, we've made progress in modeling the protein itself and aim to simulate its interactions in the near future. We also plan to develop a prototype mini ice rink and assess how the INP-induced ice may affect surface quality.
Our team has also begun reaching out to ice rink operators to understand the challenges in refrigeration, as well as to assess the applicability of our project. Currently, we are designing a citywide survey to gauge the public's understanding of the processes involved in maintaining these spaces, with a focus on regular ice rink users and players. We also plan to host interactive workshops for youth in our school, educating them on the issue of ice rink maintenance and encouraging them to begin exploring potential solutions.
Our proof of concept is backed by existing applications of ice nucleating proteins, or INPs. These proteins are already used in ski resorts to generate snow, demonstrating their safety, effectiveness, and commercial viability. In ice rinks, IceMax has successfully applied INPs from P. syringae to maintain surfaces, achieving a 22% reduction in electricity consumption. Our project plans to improve this model by using E. coli, which is easier to cultivate and eliminates the risks associated with P. syringae, a plant pathogen, producing a pure and more efficient product. We aim to engineer E. coli to produce and secrete INPs by optimizing the protein's N-terminal and removing its membrane-bound regions. This will enable the production of a pure, structurally optimized protein for aggregation, which can efficiently promote ice formation at higher temperatures when applied to water.
Over centuries, ice skating has become a cherished Canadian tradition, connecting us with our culture, identity, and each other. Yet, with the growing environmental and financial costs of maintaining these rinks, it's crucial to take action to ensure their longevity. That's why we present Innoskate, a solution to preserve our rinks, reduce energy use, and keep winter sports alive for future generations.